Yeah, I'm going to make a quick video. It might be filled with errors, but hopefully not too many. And if they are, please count them out, because this is a response on somebody's faux pas. The person who made the faux pas is Viced Rhino. Hopefully I'm pronouncing his name correctly. It looks like it's Viced, but I hear Vice, but then again my ears are screwed up. Anyway, the video, I'm going to give a clip to it and links and all that type of worse stuff off. It's Evidence for God Part 1, where he's talking to a guy by the name of Mike Riddle. And I left a comment, rather extensive comment, which I'm going to talk about. And put the comment on the screen here. Anyway, Riddle starts talking about infinity as if that's really pertinent to what is really talking about. It really isn't, but that's another story. And Riddle says, uses this as a mathematical definition. It says, existent beyond or greater than any arbitrary number. And then Mr. Rhino, anyway, Mr. Rhino, Rhino 1H took exception to that definition, and unfortunately Mike has it pretty close to what's going on here. Let me elaborate. Let's say you have a sequence of real numbers or complex numbers. Complex gets a little bit trickier because you have to worry about numbers across the plane. But let's say you have a sequence of numbers. A1, A2, dot, 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 AN, dot, 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 dot. I'm going to go for a... okay, so you'll be able to see this. Say this is sequence AI. I starts at, let's say, 1 and goes off to whatever that is. Propeller there, infinity. Goes toward infinity if for every let's not use jargon here. If you pick an N, and if you look in Wikipedia or someplace like that, we'll say natural number. It doesn't only have to be natural. Pick a number N. Could be a real number. Then I'm going to use a strict definition. There are other definitions that might be a little bit looser than this. Then for each I greater than some k, a sub I is greater than n. In other words, you give me a number, I'll be able to find some place in the sequence here where everything greater than that is bigger than the number you give me. You give me 13,767,000 da 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 0.23. I'll be able to find some point in the sequence where everything past that point's bigger than your number. Even if your number is a googolplex. And believe it or not, googolplex is a number. So, that's very similar to what Mike says, and that's basically the definition that's used in calculus books for a sequence being unbounded, i.e. going toward infinity. Unbounded and going toward infinity is the same thing. In complex variables, you have basically the same thing, only I'm going to draw it out for you a little bit. I mentioned my comment about stereographic projection. If you're interested, please look that up. That's really neat. That's where you put a sphere on top of the plane. In 2 dimensions, it's where you take a circle. Well, there's 2 ways of doing it. The thing I give actually has it at the equator, but take a circle, put it on the line, the point there. I know I have a little bit of thing above it, and then you can map every point from the plane onto the circle. And you can do the same thing with a sphere. I mean, enter everything on this line onto that circle. And you can do the same thing with a sphere, like that, marching through the North Pole, except for the North Pole itself. That gets mapped to infinity. So in a complex plane, although it looks like it can go different directions, you can have the point at infinity, which is the thing that gets mapped back to that. If that doesn't make any sense, don't worry about it. Look it up. Figure it out. There's a link there. There's other things. Look up stereographic projection. It's really cool. You can also look up Riemann's sphere. And for those who are really interested, Alexandorf one-point compactification. I really love that term. I'll say it's silly. Alexandorf one-point compactification. It uses what's known as a stereographic projection to make the complex plane into a compact thing. Anyway, so that's a very common way of treating infinity. And it's done in calculus all the time with infinite sequences and stuff like that. To reverse the definition is when you get convergence. Okay? Now, so that's one thing that he says, that's fine. Now the problem is, Mr. Rhino here really went down a rabbit hole. And I'm going to try to bail him out a little bit. Well, not bail him out, but show him where he tripped up. What he mentions is that if you have, let's grab a brand new sheet of paper here. Even have a, yeah, doesn't matter. The real line here. 0, 1, 2. You said that they're, okay, these are finite numbers, right? 0, 1, 2. He just mentions 1 and 2. These are finite numbers. 3 is also a finite number, by the way. Okay, but between 1 and 2, there are an infinite number of fractions. Okay, what's fraction? I assume he means a rational number, like 1 and 1/2, and 1 and 3/4, 15 sevenths, stuff like that. Rather than something like pi over 2. I mean, that's a fraction, and it sits right in that interval, but that guy's not rational. Don't believe me? Try to talk to a pi sometime. You'll get the weirdest answers. Anyway, so there are an infinite number of these guys sitting here. And then he says that 2 is greater than that. You're mixing things. You're mixing ordinals and cardinals. Now for finite numbers, there really isn't any difference. Now, what ordinals are, a way of counting things. This is the 0th item in the list. This is the 1st, 2nd, 3rd, 4th, 5th. Those are ordinals. You're counting. Boom, 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 boom. This is cardinal when you say there's an infinite number. Now, the thing with finite, although this is the second thing, well, 0th, 1st, 2nd. This is the second thing in the list. If you count 0 as the 0th thing on the list. It's the ordinal number 2 is the same as the cardinal number 2. So with finite things, it almost always doesn't make any difference whether you use ordinal and cardinal. Arithmetic's the same. I would like to see an example where it's not, but for most purposes, same thing. Ordinal, cardinal, doesn't matter. Okay? 5 people in a room. You go 1st, 2nd, 3rd, 4th, 5th. Same thing. 5 people, and you can count them, and that's the ordinal part. But the I mean, sorry, you count them, that's the cardinality of it, but you list them, you know, put little numbers on them, that's the ordinal part, okay? Now, as far as infinity goes, it's a little different. Now, what I want to do is, this is where I'm going to get into some place I'm a little bit shaky, and that is talking a thing, I'm going to pull it on Wikipedia, you should see this page here, and it defines ordinal numbers. And what it is, okay, this thing called the empty set. The empty set is the set that does not contain anything. And it's denoted by that. No elements, nothing. You call that 0. Now you look at the set that contains the empty set. Well, I'm going to do it this way. Set that contains the empty set, union the empty set. What does that equal? That just equals the set that contains the empty set. And you call that 1. I'm doing this union thing for a reason. Now you take the set that contains the empty set, the set that contains the empty set, and that equals just what I wrote there. That equals 2. And you keep on going. So you'll see it on the Wikipedia page about von Neumann definition of ordinals. Okay? And it goes all the way up through 4. The empty set, the set that contains the empty set, the set that contains the empty set, the empty set, the set that contains the empty set, and the set that contains the empty set and the empty set. You know, you just keep on going. Like 3 is this guy, and this guy, and this guy, like that. Oops, boy, can I? It's not right. Now, and using that definition there, it's in a way it's clumsy, but in a way it's nice because it's pretty well defined. You know, there's not a lot of wiggle room there. Okay, so it's on solid ground. So what you do now? Here's where I'm getting a little bit. Okay, so you define n this way, and what you want to do is it's going to be the set that contains n plus 1, and I mean, I'll put it this way. Each integer is an n set, so I'll say that define n to equal n plus 1, I'm sorry, n minus 1, you know, the thing that came before it, like that would be 2, union the set that contains n minus 1. So that's the way you make n. Okay? What happens if you take a union all n of n? Well, it's not a finite number, which I wish you should actually explore why. What you do is a proof by contradiction. You just assume that it's a finite number, and then what you can do is you'll find out that if you assume that it's a finite number, then it contains a successor. The successor of 2 is 3, the successor of 3 is 4, the successor n minus 1 is n. So it can't be the number itself because it contained its successor, okay? So that's an infinite number in quotes if you want to. And you call that omega. Well, what happens if you look at omega plus the set that contains omega? That's not omega anymore. What that is, you call that omega plus 1. That's the second ordinal. If you have first ordinal and second ordinal, and you keep on going, building up like that. Now, cardinality is the size of a set. And with ordinals, it doesn't matter. Like this, what's the size of 0? 0. Size of 1? 1. Notice how the size here, which is a cardinal, is the same as the ordinal. When you get to here, the size of this thing, it turns out that the size of this thing is the same as the size of that thing. The size of omega, which is the cardinality, is the same as the size of omega plus 1, which is, so the cardinality of both those sets, which are different sets, is the same. And the way you do that is you set up a function between omega and omega plus 1 that will map one onto the other. That's your homework assignment. I will not grade that. Anyway, the cardinality of omega, that's not a W, that's an omega, is equal to this neat little symbol. And, whoops, I'm a little bit nervous for some odd reason. Aleph null. Now here we go. I can do it correctly. The cardinality of omega, and I'll use absolute value signs to do that, is equal to Aleph null, which is a Hebrew symbol. The cardinality of omega plus 1 is also equal to Aleph null. The cardinality of, you can have 2 times omega. For example, in this thing here, where he says you have an infinite number of rational numbers, you have Aleph null number of fractions here, rational numbers between 1 and 2. You also have a Aleph null number of fractions there, or rational numbers. And if you call this size omega and this size omega, then together, you know, look at the ordinal. You map them out, write them as ordinals. That's 2 omega. But the cardinality is Aleph null. Matter of fact, the cardinality of all rational numbers on the real number line is Aleph null. That's by a diagonalization argument, which is all over the place. I'm not sure I'll get a link. That is a homework for you. Look it up. Are there any other infinities? Yes, there are. For example, the set of subsets of any set has a larger cardinality than the base set. In other words, that's easy for finite sets. The number of subsets of a set containing 2 elements is, let's say, 0 and 1. Okay, that's 2 elements, right? Well, they're the subsets. You have the empty set. You have the set containing 0, the set containing 1, and the set containing 0 and 1. Okay? It is 2 to the power of that set, the size of that set. Now, turns out that if you have a set of cardinality, infinite cardinality, like Aleph 1, Aleph 0, smack, the number of subsets of that set is greater than Aleph 0. And it also turns out that the number of real numbers, which is Cantor's diagonalization argument, I used to call it Cantor's second diagonalization argument. Most people just call it Cantor's diagonalization argument. The number of real numbers, you know, like pi and square root of 2 and all that type of good stuff, is greater than the cardinality of the rational numbers. And it has given the letter C, stand for continuum. And before I really start getting too far off course here, I'm going to pause this now and try to get this thing out. Okay? Thank you for your indulgence. Have a great day.